Okay. I begin this by saying the most important of all applications of calculus is with differential equations, also known as DPQs. Apparently that's quicker to say on college campus than differential equations. So when you get into DPQs, and you can take a whole course in calculus in DPQs, that's usually what, probably about calculus 3 and 4 are probably DPQs. So this really sets up for your future, what you're gonna see in your future study of calculus. So when scientists use calculus, it's usually to analyze a differential equation. Because we know we often measure, when we're going out there and measuring something, what we're actually measuring is the rate of change of something. So that's gonna be part of my differential equation. So we're gonna model some phenomenon where changes occur, okay? And they wanna predict some future behavior based on how current values are changing. Okay, that's what it is. Generally speaking, what is it precisely? So, and this is on Canvas. A differential equation is an equation that has an unknown function, antiderivative, and one or more of its derivatives, such as this. This is a differential equation, where the derivative is actually part of the equation. We solve it when we're able to find the function, y or f of x or whatever, and place it and its derivatives back into the equation. So it's kind of like this is a variable. So why do you have to spend so much time on it in college? Because there's a lot of tricks to learn, okay, to solve differential equations. Sometimes you can't even solve them. Why is it important? Because in our world, things tend to change, and describing how they change often ends up as a differential equation. So this becomes a way to communicate. Math is the international language, and it's the language of science. Okay, so I'm just going to show you some examples, nothing to do on the first few, and then I'll really show you what we're trying to do. So example 1 on your sheet, the more rabbits we have, the more rabbits we get. I would think so. Then those rabbits grow up and have babies too. The population will grow faster and faster and faster and faster. Okay, so eventually you'll be able to model this. Here's the important parts. We want to figure out what the population is at any given time. Okay, we can give some nomenclature for that, maybe the number at any time. The growth rate, oh, how are they growing? The population's rate of change. Okay, we could actually use real numbers. We're not going to do that right now. Okay. But we know that if the current population was 1,000, the growth rate is 0.01, then we're going to get new rabbits. We're going to get 10 new rabbits next week. Okay, that makes sense. But that's only true as a specific point of time, because now your rate is going to change on the amount of new rabbits. The population's constantly increasing, so it's not 10 rabbits every week. The bigger the population, the more rabbits we get. So it's better to say the rate of change at any instant is the growth rate times the population at that point in time. This is a differential equation. Here's your derivative, d and dt, equals the rate at which something, the population at a particular point. I mean, that makes sense, right? Growing at a rate of 0.1. 0.1 of what? Well, the population, initially it was 1,000, but it won't be 12 weeks from now. I'll have a different population size. So it'll be 10% of that. And so this is an example of a differential equation. Nothing to do here, just showing you the differential. Because it has a function, n of t, and its derivative is part of the equation. There's its derivative, there's the function, and its derivative. And we can say that this is sort of the rate of change of the population over time equals the growth rate times the population. Might be one way to interpret it. Here's one I think you've seen before. Money earns interest, right? And the interest can be calculated at fixed times, such as yearly, monthly, continuously, remember all that stuff, and added to the original amount. This is called compound interest. So when you add it to the original amount, then the next time you earn interest, the pot of money has gotten bigger. So you're not earning the same amount of interest every time, although the rate might be the same every time. And that's what we're interested in, the rate might be. But that pot, and just like the rabbit population, might be growing over time. And we've got this. You may think you've not seen that before, but oh, in some way you have. That's kind of like the PERT formula. Y'all remember the PERT formula for compounding continuously? Principal times e to the RT. That's basically what this is. So, pay the rate of change times the amount of money in the pot at any particular time. Notice that's also a differential equation because it has a function, v of t, and its derivative, dv of dt. And one way to define or to explain this equation is the rate of change of your money over time equals the growth rate times the current value of that money that's sitting there. Okay, kind of seems like the rabbit one. Nothing to do there. Just want to show you a differential equation. So, pretty much like the rabbits. What else can we model? We can model the growth of a population. That's probably based on the assumption that the population grows at a rate proportional to the size of the population. And if we let t equal time and p equal the number of individuals and how big the population is, how big the pot of the population, how big the pot of rabbits. The growth rate of the population, the rate of growth, we can call it dp over time, dp dt. And that can be modeled like this. K times the population at any particular time. K seems like R. The population will be growing at a rate depending on the size of the population at any time. This is also a differential equation because we have the unknown function and we have its derivative. They all kind of look the same, right? That's kind of cool. Yeah. But that's what a differential equation looks like. And so, using integral formulas, we can see that any exponential formula of the form, of this form right here, would be a solution to that equation. This is your PERT equation. P-E-R-T. K is my rate of growth, T is time, E is not. E is a constant, right? You've been working with the solution to those differential equations when you were doing compound interest, didn't even know it. Okay, when you get into calculus in later years, you realize, well, wait a minute, there's other factors at play. Maybe drought, amount of food, natural predators. We're not taking account of deaths, things like that. Okay, well, then you put other factors in there. But this is a solution, which we're gonna see later, to any of those DFQs that I showed you before. So anything of that form is gonna have that as a solution. Anything of this form. If you wanna write that down, anything of this form, whether you call it K or R, doesn't matter. The derivative equals R times the function, N of T, P of T, whatever you want to call it. C of T. This will be a solution to this. P of T will be that. I mean, if you want to write that down. So here's the derivative. Here's the original equation. That's what we can play with. And how did we get from here to here? We just use integral formulas to get. Anything that's in that form, that's in this form right here, the first form, anything that's in that derivative form, this could be a solution. Okay, seems like a lot of setup, right? And on your handouts, there's a lot of stuff. Let's see, let's look at example. Well, let's just look at all the examples, I guess. Well, here's what we walked through. Here's what we walked through. Here's what we walked through. So 1, 2, and 3, we already pretty much answered. If you got this right there, I'll highlight it again in the notes, is a solution for any DFQ that looks like that. That's the key. Okay. Bacteria in a certain culture increases at a rate proportional to the number present at that particular point in time. If the number of bacteria doubles in 3 hours, in how many hours will the number of bacteria triple? Write a differential equation that describes this relationship, where K is the constant of proportionality, sort of the change at any particular time. Why don't we just do that part, a differential equation? Let's just highlight that. Let's just write a differential equation. Use this just to write a differential equation. Do you want to call the population of bacteria B? B for bacteria? Number of bacteria at time t. Then we can do a differential equation, dB dt. And let's see, we've got K, so we'll use K. You could usually use R. K, B of T. Okay, we're done. That's what would model this. Looks like that's what modeled the rabbits, the rate of growth for rabbits, the rate of growth for our money, population growth. All right, bacterial growth. Oh, this is a good one, the next one. They all look pretty similar to me. The problem with differentials is when you consider other factors, but we're just introducing differentials at this stage. Okay. A rumor spreads among a population of n amount of people at a rate proportional to the product of the number of people who've heard the rumor, key word, and the number of people who have not heard the rumor. If P denotes the number of people who've heard the rumor, number who've heard the rumor. Probably should have started off with N equals population size. If we want to keep it, we can say NT. Probably should put that above there. So we got that, we got P. That's the number of people who've heard the rumor. Write a differential equation that could be used to model this situation with respect to time. Number of people who've heard the rumor. That's what I'm interested in, the number of people who've heard the rumor. I would imagine that would be GP, that's what's changing, right? The number of people, really, who've heard the rumor over time. T is time. Yeah, so we got T is time, we've got that, okay, we want to use K, not R. That's dependent on K times something. Let's read back. The rate is proportional to the product of two things. Ew. Not one thing, but the product. So how this is changing, not how this is changing, but how the number who've heard the rumor is changing in terms of time, based on the product of the number of people who've heard the rumor. Well, that's P. Times the number of people who have not heard the rumor. Well, how can I express the number of people who haven't heard the rumor? I'm sure there's a shorter hand of saying who haven't heard. How can I put that in some sort of expression I can plop in there? They didn't say proportional to the population size. They say proportional to the product of the people that have heard the rumor and the people that haven't heard the rumor. How can I express the number of people who haven't heard the rumor? You were kind of on that path there, Blake.
Can you repeat?
If this is the number of people who've heard the rumor in a population, what's the number of people who haven't heard the rumor in the population?
The population minus P.
Say that again.
Like the population size minus P.
You got it. Total population minus P. That's the leftover people. So, NFT minus P. That's that differential. K, R. Sometimes you'll see K, sometimes you'll see R. Whatever you want it to be. But be careful. They didn't say it was changing with the number of people. Whereas the last one, hey, the bacteria was changing. Population of the bacteria was changing. Okay, that was B of T. This is the number of people who've heard the rumor is changing. Is that okay? Okay. So it brings us to the part you really need to know. Somebody got this that wants to get this done? Kind of, I mean, it's the same general DVP of every time. We already know what one of my solutions is gonna look like. It's gonna look like PERT that we've been using. Okay, let me see if there's anything up here in the notes I want to say. Okay, I guess I want to go all the way back here where I said. We solve a differential equation. We solve a differential equation when we find the function y, and it and its derivatives are then substituted into the equation. Okay, let's go down here again. So if we look at 4, 5, 6, 6 looks like it has somehow changed. The nature of the question has somehow changed. Okay. If y is 4 cosine 2x plus sine of 2x, if that's a solution to that differential equation, look at this equation. We've got a function and some type of derivative of that function that makes it a differential. Doesn't have to be the first derivative, but we got the equation and some type. We got the function and some type of derivative of that function. Well, we have solved it when we find the function. I've already found the function and the derivative of that function and plug it back in. Okay, well, we got this. We know what y is, 4 cosine 2x plus 6 sine 2x. Okay, well, we know that part. We can plug that back in. What I need is the second derivative. Well, I can figure that out, right? What's the second, well, I can't get to the second until I get to the first, right? Hey, what's the first derivative up here?
There's no second bell up.
Cosine 2x multiplied by negative sine.
Close. Say that again.
8 cosine of 2x.
Okay, I got the 4 here, right?
Yeah.
And then I can take, because any constant I can just pull out, right? I can pull that out. What is the derivative of
Oh,
sine?
negative sine of 2.
Negative sine.
Multiplied by 2.
Negative sine of 2x. Oh, and then I got an inside part.
2.
Derivative of the inside is 2. Yeah. So that part's what, negative 8 sine 2x. But then we got another part here. We can pull the 6 out. What's the derivative of sine?
Cosine
So there's cosine
times 2.
of its thing. Oh, there's an inside part, so I got a derivative of the inside is 2, so that'd be plus 12 cosine 2x. Well, that's the first derivative. It's asking me, that equation, that dvq has a second derivative, so I gotta figure out the second derivative here. I bet that's gonna be cosine, right?
Yeah.
Well, not 2c, there's no 2c for cosine. 2x, and then I'm gonna have to take there's an inside function again, right, times 2. And I got the negative 8 out here. So that's negative 16 cosine 2x. But then there's this other part.
So, negative 24 cosine.
Yep, I'm gonna have negative, this is gonna be negative sine 2x, and then there's an inside part 2x, so there's gonna be a 2 out here, and a negative, negative 24 sine 2x. Negative 24 sine 2x. Here, for the sake of the video. Negative sine 2x, and then times the derivative of the inside part 2. So negative, and the 2, negative 24 sine 2. Okay, that's the second derivative. We have solved a differential equation when we find the original equation. Got it. It was actually given to me. And the derivative, or whatever derivative. It doesn't have to be the first. This one was the second derivative. So then I've got negative 16 cosine 2x minus 24 sine 2x plus 4 times the original function. And I can clean that up a little bit, right? Let's see, I've got negative 16 cosine 2x minus 24 sine 2x. I got this 4 out here times both things. That's 16 cosine 2x. And plus 24 sine 2x. What do you notice?
Cancel out each other.
Minus 16 plus 16 minus 24 plus 24 equals 0. 0 equals 0. Hey, it worked. If it said that equation equaled 16, we haven't found the solution. Because 16 don't equal 0. And we know this part equals 0. That was a solution. We have solved a differential equation when we find the original equation and the form of the derivative and plug it back in and make sure it works. Because remember, we got an equation, not an expression. We've got an original equation. A DPQ, differential equation, it's going to equal something. So down here, number 7, does anybody want to, has anybody got this? Who wants this? I guess it'll be on the video. So, okay, let's look at number 7. Then we'll only have one more after that. So let me scroll up. This one says, let's determine whether the given function is a solution to the differential equation. This is not a multiple choice question. It is a 3-part question. Is this a solution to this equation? If I, let's see, minus f of x, in this case f of x is minus cosine x. Looks like I'm going to have to figure out the second derivative of whatever f of x is, right? What's the first derivative?
Sine.
Minus sine? Sine?
Mm-hmm.
Yeah, because it's going to be minus sine with a minus in front of sine. And then I got to take the derivative of that one,
Cosine.
and I get cosine. Oh, so the solution is when I find the equation and the form of the derivative and plug it back in. Second derivative minus the function should equal 0. So cosine x plus cosine x equals 0. Is that true? Is that a solution to this? No. It is not. Oh. Well, what about this one? What's the derivative of 2e to the negative x?
Negative 2 e to the negative.
Negative 2 e to the what?
Negative x.
Negative x. Yeah, it's this thing, and then, oh, it's not just 1x, so derivative of there was negative 1, which made the negative in front, so we'll do the second derivative.
2e to the negative.
Yeah, 2e. I'm gonna have, that's just gonna be e to the negative x, and then derivative of the inside is negative 1, which makes that 2e to the negative x. Okay, let's plug this in. Let's see, second derivative was 2e to the negative x minus the original function, which was 2e to the minus x. Does that equal 0? Hey, yes it does. That is a solution. That one worked. Doesn't mean that you can only have one solution. Now, if we remember anything about integrals, it's like we can do any antiderivative. There might be others. Let's see. What's the first derivative of this one? That's not little k, that's capital K, which is constant, because we're doing the derivative in terms of x.
I'm saying just k to the e.
K e to the x. That's a constant, so I can bring it outside. Derivative of this, e to the x, times the derivative of the inside. Just one. Okay. The second derivative.
Same thing.
Same thing. And we can bring the k outside. E to the x is e to the x times the derivative of the inside, which is okay. Hey, let's plug that in. See if it works. Second derivative, which was k e to the x, minus the original function, k e to the x. Wonder if that equals 0. It does. This one is also a solution. That's what we'll be wanting to do when we do DVQs. Find the original equation and whatever form of the derivative you need, plug it back in, see if it works. Because right now they're kind of giving me the original equation. Sometimes we might have to find the original equation. Be okay on that? Okay. Number 8 is a multiple choice question. So the equation that's given to you there, number 8, is a solution to which the EQ, A, B, C, or D. I'm gonna let y'all figure that out, but I'll give you the right answer. Now I got a differential equation, derivative, original function, form of a derivative, original function, form of a derivative, original function, form of a derivative. Oh, they're all differential equations. This one is multiple choice.
What's the answer?
Oh, I'm gonna wait till. Well, there's only 4 of us here today. Hopefully we don't get a tie. What do you think the answer is?
A.
Gotta vote for A.
I haven't
Huh?
finished. I haven't finished.
Okay, go ahead. Because we don't have a majority yet.
I think it's A.
50% of the class says A. We need UV here to break the tie. Or Evie, what do you think?
Mr. New,
Hmm?
did you forget to put -5?
I sure did.
That's what I did.
Yeah, because it disappeared here. It was still here. Hey, if it's multiple choice and the first one worked, I mean, you can double check. The other 3 ain't gonna work. That's differential equations, guys. No, it's not. I mean, that's what they look like, but we'll work with those. There might be like a multiple choice question, which just like these, because I basically kind of got these from College Board. You know, which one is the following is a solution to this differential, or which differential equation works, something like that. I think fairly simple if it's just on this lesson. Count on 1 multiple choice, like this. Hey, but 1 is 1.
So for like, will we have to test every single solution, like an actual test, or is it like a shortcut?
If it's multiple choice, as soon as you find the answer, that's it. But it could be the answer was D. If you're sure on A, B, and C that they were not, then you could just choose D and move on. But usually, if you're like me, I'm gonna test D, because the first 3 didn't work. But you know all the multiple choice answers are not D, so you'll get answers. You don't have to test everything. So that's it. I will not be here tomorrow. So what you get to do is just practice.